So yeah, hello and welcome to this video. We're gonna talk here about the difference between the heap and the stack, and this is one of the things that I actually do really love in computer engineering, as they for me were nothing at the beginning but two data types or data structures but like they were for me like not really of a difference. Like I was like usually questioning why was there two different things that just does the LIFO or the FIFO or these weird abbreviations, and they are just of the same thing. Like you can insert and exert, and why is there two different things? But this has became clearer for me when I have understood the memory structure and the RAM structure and how does it store our variables. So let's start this off by declaring a code on a mid to high level language like C. Let's say we have tried to do an integer x is equal to 10. And let's also declare a class like p is equal to new person as Bob. So when we do that and execute that at the terminal, it will just work. It will just not give an error, or just nothing fancy will happen. But where does these actually go? Like, where does this data and this data go? Are they are not of the same value. This stores integers. What does this store though? Does this store in a stack or a heap? Like, why do they both even exist? So a lot of beginners computer memory is just like a magical black box, just memory coming in, the data coming in, getting out. So actually here data lives and the program run, but like it's more than this. Like the processor needs to know where are this data being stored and how am I supposed to process it, until you can't anymore, because it start to get dynamic and fancy inside. So until your app crashes after running for 3 days straight up because of a memory leak, until you hit a recursive loop or a crash on your browser, or more immediately until your professor asks you for an exam, explain the difference between stack and heap allocation, your minds, or my mind especially back then, were like completely blank. So now we are going to try to open this black box and going to visualize exactly what happens in your RAM when your code runs like this one, and we're breaking down the stack versus heap way. And let's dive in. So before we split things up into stacks and heaps, we need to have a big picture of what's going on in a stick of a RAM, or your computer RAM RAM stands for random access memory. Yeah, random access memory. So but why is it random and access? Like why? Yeah, we get it that it's a memory, but why is it random and access? This random access makes it cause that our data is not being stored in layers, not only layers. Like it's not a big room or a house or a building that each cell stores the next 1 plus 1. It's not usually that case. It's not always that if here is 1, then here is 2, then here is 3, here is 4. So yeah, sometimes we want to store some things. We don't want to just store a big block here. Sometimes we want to remove that. We want to remove a name, for instance, so we want to remove that. So we need this data to be dynamic, this storage place to be dynamic. So in order for it to be dynamic, we need to use the correct data type. So if we want the data to be next to each other, we usually allocate in a stack. Stack allocates everything next to each other. So let's say we have integer x equals 1, integer y equals 1. So here in a stack, the first thing in a stack here for me is gonna be integer x, yeah, of the size x and a value of x of an integer type. Same for y. yeah, so here is also y, but until, and just goes on whenever I allocate a new value. But let's say I made a new form. Yeah, this form of a data type, let's say it's a class, so this class or struct or whatever you can allocate a place in memory can be created, yeah. But when I created, I didn't create integer x equal y equal x equal 1. I just assigned a name to a value 1, but I didn't create 1, neither I have created x. But here I've created something called form, and I've created form 1. So when I create something, this thing that I have created, I can also delete. Anything I can create and delete cannot just take a block in my memory. Why? Because sometimes I want to add things to this object. Say if like I assigned, let's say A and B, here is a stack, then I assigned a class here, then I assigned C. Say now I want to add this class size, I want to increase this class size. Now I need to be able to access a new place. This place is not sequentially next to me. That if it's sequential, we are supposed to access through a stack. If it's sequential, yeah. But if it's not, if it's dynamic, we use heap. So things that are allocated dynamically use heap. Things that are allocated statically as or like sequentially use stack. So here comes the question: why not always use a heap? Like say heap now is like it's simpler. We just can allocate wherever we want, and we can allocate A, B, and C there, and G wherever we want. We can have as much size of memory we want and allocate from anywhere we want. But here comes a question or the problem, which is a very big problem in usually in computing, which is performance. So performance for me is a crucial point here. So when we allocate, for instance, things that are away from each other, we need to search. We need the processor to search me each value of these, like class, where is its extension? It's there. Where is another extension? It's out there. And where is another extension? It's out there in the memory. So yeah, it gets more messy, and this makes the processor even needs more cycles to perform simple things like even addition or subtraction over two classes. Yeah, so that's why stack here is better for me as a performance, because it's sequential. But heap here is for things that I want it to be dynamic. Stack here works in list, like let's say list in Python. List in Python is in heap, but stack here is like array in C. It's also vector here, vector in C. So yeah, so list or vector you can allocate the size as you want. You can delete, you can add, you can even remove this struct. But in a stack is of a static size. You allocate at the initial of the size. We allocate a place in the RAM. So that was the first part. Second part, as a data structure, the stack, as you can see, is formed as a sequence going up, like, or going down, if dependent on the architecture, like 86, as I remember, was from up to down architecture, and the microcontrollers on other microcontrollers. But as for us, an x86, we usually go to up, but the main idea is that we go sequentially. Like let's say you assigned window, you assigned x equal window, and y equal person. You can assign window, then assign person. The RAM does store these in window. Assigns the first place to be window, assign a person to be x to be person through their values. Also, x and y, for us to understand, are nothing but pointers here. Okay, so x is stored as a pointer to this location. I don't wanna. I know people hate the pointer, but it's fun. Like pointer is nothing but look. I think that points here, like yeah, x, y points to this value, which is window. Also, when we say array of 5 equals to let's say 1 2 3 until 5, so the array is starting from 0 until 5, so it's this first value is array. This value itself is the name array, yeah, so we're calling it array or x, so the first name is x. This one is x plus 1, yeah, and goes on to be x plus 2, x plus 3, so because array is on a stack, so it goes the second, this is the second plus 1, this is third plus 1, this is 4 plus 1 plus 1 until we go to the maximum size, which is from 0 to 4, yeah, from it's x plus 0, x plus 1, x plus 2 until x plus 4. Yeah, so as you can see here, stack it goes through the program, allocating places, allocating things, but heap allocates things dynamically. Things can point to each other to form a class. Like say if I class, this is a class, like it contains name, like student, class student can contain name and can contain age and can contain ID, yeah. So this is, for instance, a class. I can remove from this class, I can remove from this class, and I can remove this class itself, like and I can point on itself, yeah. So heap here is more dynamic, more active than a stack for me. When we go even more further into the memory structure, we will find that our RAM, this is like, say, this is considered, you can consider it the chip of a memory, like the memory we can see, or the RAM we see, which is, yeah, it goes like some chips here and some connectors and the chip and the controllers out there in the memory. So this this memory is then assigned to be on this form. So when a processor runs, or when a computer, you start a computer, you run the OS kernel. What is the OS kernel? It is a software that runs the drivers like mouse, keyboard, let's say speakers. All of these are run to the operating system here, like here in this part, and is allocated on a place in the RAM. So that means, it also means, like it's out of this course, but I mean if you disallocated or have disconnected the hard drive, you can still run the processor, or still can run the operating system. Some people think like if you remove the hard disk out of your computer and the processor or the computer will fail. No, at all. The fact is that after, let's say if you have Linux, for instance, on your device, so the Linux on your hard drive gets to run, it passes first by the BIOS, then after it runs by the BIOS, it gets to the Linux, and then the Linux gets stored to the kernel, doing the functionalities here, yeah. So that means if you remove the hard disk, the processor and the system will keep on running. It's already running on the RAM, okay. Yeah, it won't perform as functional as if it was connected to the hard disk, but it can be 100% run on just the RAM. Then after that, after we have took the segment of our RAM to be running the kernel and the OS, it can then start running the programs. The programs here, other than the kernel, yeah, the programs here can be programs of a heap structure, which usually is pointing upwards, and a stack structure, which we have said at the beginning, that usually points at downwards. So heap extends as the program on run. When it's running, let's say the program is running, so the heap keeps extending and on getting removed, freed, and doing like that within when we are running our processor. Now, like let's say we are doing nothing, things are happening. Heap is getting bigger and slower. You find that your memory is getting higher and lower, yeah, but yeah, by small variance, but it's changing nevertheless. Meanwhile, on the stack, The stack is when the program on like what they call on compiling. When you compile the process already, say you run the process, the code already, whenever the process allocates something, it allocates already my x is equal 5, my x equal g, my x equal whatever, my equals 6. So yeah, it gets stored to the stack. Meanwhile heap, and this stack stays usually constant by the program, but heap is my dynamic allocation, so things gets removed, gets added and so. But again, the stack is way faster than the heap. You already know that the second thing allocated after it is it's it plus 1. Yeah, it's it plus 2. It's minus 1. Meanwhile, heap is you need jumps and you need get to and you need searches and so on. Then there is segments of the memory here that's usually out of the course of this heap and stack part, but we can talk about it. That this is there's when we run like the pre-processed functions, like let's say hash include or hash define or hash in a language like C, we will find that there's things for processed data, especially when you say, let's say int x won't give an error. In some languages, yeah, it won't give an error, but it's uninitialized or unassigned. There it goes to the BSS segment. Here, all the uninitialized data comes in place. It's stored here for the uninitialized, not in stack, not in heap. Also, things were pre-processed, it gets initialized in data. Things like comments, like hash in comments in C, for instance, is like with this sign and this the double backslash, it gets stored to the text. Let's say if it was for instance in Python, it's the hash, if I remember. So yeah, it gets text in the text segment. It's just for the text. Yeah, it's not something to be processed, and that's usually a small memory. Something here, it's more of a text here. It's nothing but like I'm trying to show that heap here is like in the transient data object, like things that like adds new, delete, containers for STL, like in the vector and the heap, and the things that are dynamic, things that are exceptions, like they are already deferred by program. Yeah. Local variables. This was for the stack, for the heap. Now for the stack is for local variables, something that will always be local. Yeah, something that will always return addresses, something that is a function argument. It's like it returns 2, like function 2. It's always a 2. Yeah, it's always there is a location here for a variable. Yeah, compiler temporaries. Yeah, the things in compiling, and interrupt context, things that interrupt, like int3 and int5, things that are stored into the doing interrupts in the process is usually in the stack. Yeah, doing interrupt for keyboard, for instance, like a keyboard function, like keyboard, when it says, like let's say you type an I on the keyboard, then this I is doing an interrupt of a certain number, and this interrupt is sent to the processor, and the processor interrupts the sequence of its action to do that keystroke you did. Then we have set the BSS. It's for the, as we said, for things that are initialized or initted. Yeah, as the init. Yeah, initialized. And this is the data for things that are initialized, which we have talked about there. Yeah, this is always a famous picture for it. Like it tells you that low address, like things in the process, in the RAM, as we said, in the structure of the RAM, we will find that the things in low address, like if you try to in C, for instance, if you try to see out a pointer pointing to a certain address, like say hexa A, B, C, D or something, we will find, if you tried to access on lower memory, very low, you will find the kernel. Above that, you will find the text, the code itself, the words, the comments, and so on. The data, then you will find the data itself. The like x was equal to what? To 5, to 6, to 7. Yeah, it's gonna be found here. If things that are initialized to 0 or whatever was not even initialized, Usually things that are not initialized are assigned to 0 or initialized to garbage value. So it's stored here in the BSS. Then there is the dynamically allocated data here in the stack and the heap, running by the process. As we said, the stack gets things after each other, and the heap is of dynamic allocation. And this is our virtual memory, which means that this is the we are not talking here physical memory. We are not talking each address. Actually, we are talking like what the progress or the process itself sees, or like through the memory or the programs running. Yeah. So also here is like some text talking about that there is a difference between stack and heap in pros and cons. Like we'll conclude everything we have said, that the stack is very fast access since it's sequential. Yeah, it doesn't have to explicitly deallocate variables. Yeah, it's already of a certain size. You don't want to use that variable, don't even use that variable. Space is managed efficiently by the CPU. Memory will not become fragmented. Yeah, it's already, as we said, it doesn't need to search for variables. Yeah, here's usually used for local variables only, since it can have the access to point for another variable next to it or before it or beneath it. It has a limit on a stack size. So this is dependent on the OS. Like there's sometimes you can have Windows 60 Windows 86-bit, or you have Windows or 86-bit, but Windows 86 usually have 32 bits, and Windows like x84 46 has 64 bits. Yeah, we can usually extending the bits is not something that is really good, but especially that it needs a complicated architecture. But for most of our usual systems now in the market, is usually over 46 bits. Yeah, so it has a limit on the stack size. Yeah, as we can said it's dependent on the OS, and a variable OS, which is operating system, of course. Variables cannot be resized, as we can say. Yes, we said that we cannot resize it. Just leave it there. Yeah, but on the other side, the variables on the heap can be organized, accessed globally. You can just point to another place on a memory, or even another memory, another slot of memory. Yeah. No limit on memory size, relatively slow, but this is the main problem here, that it's slower access. You need to search, or you need to find, or you need to have the access for another location, which CPU intensive. No, that's why usually games that has that's usually how they optimize games, by the way. Like other than that they do things that to be static, not static visually, but static as static, but like they don't need to each hammer, like someone is hitting something with a hammer, it doesn't need to initialize each position by an angle. It doesn't need to do each movement. Yeah, it just can allocate that it goes from angle A to angle B, and does a gradient of -1 or something. This is better for the memory and for the processor than just doing it it's something that initializes each time differently. Yeah. So it's not guaranteed to use efficiently the space or the memory, and may become fragmented. That's why sometimes people really contradict that the Python, or like don't really like Python. Python, they say Python is bad, inside Python is not bad, but it doesn't teach you to how to efficiently use data, efficiently use your memory allocations, since it usually has the list or the matrix to be on TensorFlows, just to initialize as much as you want. So it's not as the other languages used for the hardware, like C, C++, and Rust, and these languages that are focusing on the hardware and how much will I take, or even the ARM processor, what do they call it? Yeah, the assembly, ASM. Yeah, the assembly that is already the lowest thing you can write after the binary, the lowest thing, highest thing after the binary. Yeah. So yeah. So, and this assembly has too many versions, by the way. Okay. So you must manage this memory. You are changing from allocating and freeing variables. That's you must manage it. If you don't manage it, you're not using its full power, its full capabilities. And variables can be resized using reallocate. This is if we're talking C. There's things like Python and other languages has different language commands. So yeah, this was the comparison between the stack and the heap and some other things that I hope that was useful to you. I hope that this video was useful, and I hope if there's another question that would be related to this or can make me improve, I would love to hear it. And thank you very much for your time, and see you on the next time. Thank you.